Today we're going to be talking about some of the subtler issues involving similar triangles. So we've already demonstrated in another video that if we have two triangles that are similar, then they are proportional. Let's remind ourselves what exactly this means. Similarity means that they have equal angles. So this angle at A matches that at D, this at B matches that at E, and this at C matches that at F. So if the angles match, then the sides will be proportional. So what that means is that this length AB divided by this length DE, which looks like a factor of about 2, is equal to the ratio AC over DF and is equal to the ratio BC over EF. So we get an equality of ratios between edges of the triangles, that's proportionality, as a consequence of the equality of angles, that's similarity. But what about the other direction? What if the sides of the triangle are known to be proportional, but we don't know anything about the angles? Can we conclude that the angles are equal? This is called side similarity. We're trying to use the sides of the triangles, not side in the sense that the sides are presumed equal, of course, but that the sides are presumed proportional in this sense that we just described. Then if they are proportional, are the angles necessarily equal as a consequence? And there's another tool of similarity that we will use that's related to this. It's called side similarity. What if instead of the proportionality between all three edges, like this edge divided by this one matches this edge divided by that one matches this edge divided by that one, what if instead of all that, we have only a proportionality between two? This edge divided by this one agrees with this edge divided by this one. Then if we also know for some reason the equality of an angle, angle A equals angle D, then we have a proportionality among the edges together with an angle, and that's called the side similarity criterion. Then from that, can we deduce that the triangles are in fact similar? So we're going to be proving both of these statements in the same video today. I'm going to focus on side similarity, but side similarity is going to be basically the same construction. So the secret to proving both of these things is to construct an auxiliary triangle, which shares some of the properties of ABC and some of the properties of DEF. I'm going to gradually unhide this thing. So here's what we're going to do first is we're going to construct a segment DE which matches D prime E prime, which matches the length of DE. And for simplicity, I'm going to assume that these are parallel, but for the sake of argument, this thing will match DE in length, but it will be parallel to AB. Okay, so it has in common something of the angle of AB. It's parallel to AB, but it is equal in length to DE, and that's why I've made it green here. Now, after I've constructed segment D prime E prime, which matches the length of DE, then I'm going to make two angles, but I'm not going to make them to match the angles here. I'm going to make two angles which match angle A and angle B. So let's see if I can get this right on the first shot here. So these two angles, and I'm sketching them in orange to indicate that they match these. Obviously, they're not the same as each other, but this angle at D prime matches that at A, and this angle at E prime matches that at B, and that's why I've indicated that they're in orange. They share something with this left triangle here. Now, on the basis of these angles, we can draw lines out from them and find the intersection point of that line, and we'll call that F prime. Now, that gives us a new triangle, and it shares something in common with DEF, although not much. This length matches this length DE. It shares something in common with triangle ABC, only two angles. It's not, obviously it's not congruent to this guy. It looks like it might be congruent to this guy, but we don't have enough information to say that it is because we only have one side in common. We only have two angles in common with this triangle, but two angles is enough because they add to 180. So that allows us to conclude that this third angle F prime must be equal to this angle C here. Now, what good is that? That doesn't look like it's likely to be much use to us. What can we say about this? Well, it matches all of the angles of the triangle ABC. And if so, well, it must be proportional to the triangle ABC. Now, what does that mean? That means, for example, AB over D prime E prime must agree with AC over D prime F prime. So let's write that in text here. So as constructed, I'm not going to write all the steps of this proof here, but as constructed, AB over D prime E prime matches AC over D prime F prime. So that's something that we know about this triangle that we've constructed. And why do we know it? Because we rigged the angles to force it to be similar to the triangle ABC. And so if we know that similar implies proportional, then we get this statement. We have one more equality that is similar, and for exactly the same reason. If the thing is similar, then we can also say that AB over D prime E prime is equal to BC over E prime F prime. So that's another statement, similar in nature. So we get the equality of these ratios. Now, the nice thing about D prime E prime is that it exactly agrees with DE. So AB over D prime E prime is the same ratio as AB over DE. Now, in the case of side-side-side similarity here, we're assuming that the orange triangle is completely proportional to the green triangle. And so we're already assuming that AB over DE is equal to AC over DF. If it is likewise equal to AC over D prime F prime, the only possible explanation for that is that D prime F prime agrees with DF, right? If this equation here is true, and D prime E prime agrees with DE, and this equation here is also true, then the only thing in play here is the df and the d prime f prime. Those must be equal to one another as well. And so we get a statement about this, which basically, I think the easiest way for me to sort of represent this is to change this thing to green. So let's change that to this green color. So that's basically a representation of the fact that we've demonstrated that d prime f prime must agree with df. Basically, whatever ratio we have between ab and d prime e prime, that must agree with the ratio between ab and de, but it is assumed to also agree with the ratio between ac and df by the assumption up here, and by proportionality, it must agree with the ratio ac over d prime f prime. So that forces d prime f prime to agree with df in length. Now, that's a lot to know. It still isn't enough to tell us that these two triangles here are congruent. It's almost enough, but it's only two sides. So we still don't have congruence between these two triangles. But I can make the same argument to identify that e prime f prime must agree with ef. And if I make that argument, as is suggested here by the third equation in this first question, if I make that argument, then I get these things congruent by the green information, the side-side-side congruence information. Now, if I don't have this third equation because I'm in the second case, then I might also know that angle A equals angle D. If I know that angle A equals angle D, then I know that angle D prime also equals angle D. And then I know that these triangles are congruent, these two on the right are congruent, not because of side-side-side, because I don't end up knowing the black length, but because of side-angle-side, because I know I have a match of these angles. So you see, these hypotheses, whether I know the full proportionality of all three sides, and therefore know that E prime F prime agrees with EF, or whether I know that angle A equals angle D, and therefore conclude that D prime equals angle D, for one reason or another, I get a congruence between the two triangles on the right. And so in either case, I'd like to record that. So for either question, we deduce that triangles DEF and D prime, E prime, F prime are congruent. So in one case, side, 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 in the other, side, angle, side. So that's a conclusion that we can make from this information. Now, what good does that do us? What are we trying to do? We're trying to show that the original triangle in green, DEF, and the original triangle in orange, ABC, we're trying to show that those are similar, meaning that they have equal angles. Well, the angles in D prime, E prime, F prime are rigged to agree with these orange, and the angles in DEF are the original in green. Once we show that these two triangles are congruent, then we get the equality of angles. This angle D prime must agree with that of D. This angle F prime must agree with that of F. This angle E prime must agree with that of E. But these were the original angles from this triangle. So in other words, angle A matches angle D, angle C matches angle F, angle B matches angle E. And this demonstrates that the angles in this orange triangle must, after all, agree with the angles in this green triangle. In other words, if the triangles satisfy either of these two conditions, then they are indeed similar.